Welcome to this module, and in this module we will be looking at how we can grow silicon dioxide and what are the characterization method to understand or to measure the thickness of the grown oxide. In the last module what we have seen? We have seen the importance of silicon dioxide, or you can say the application of silicon dioxide such as a masking oxide, a gate oxide, pad oxides, and also it can work as a mask against diffusion, against dopant, right. Either it is a diffusion method or it is a ion implantation method. So, we also saw how we can grow oxide depending on the either we are using a wet technology or we are using a dry technology. So, that means that if we use vapor then we have a wet oxidation, if we just use oxygen we have a dry oxidation. And advantage of dry oxidation over wet oxidation when it comes to the quality of the oxide. Now, again in wet oxidation and dry oxidation the growth is done in a furnace. It is done at high temperature around 900 degree centigrade to 1100 degree centigrade. So, when you talk about furnace, if the furnace is vertical it is called vertical tube furnace, if the furnace is horizontal it is called horizontal tube furnace, alright. So, this is done in a horizontal tube furnace. So, if you see the screen you can see thermal oxidation methods. The first one is a dry oxidation, where you can see that when we have to load, first stage is you have to load the wafers inside the furnace. So, when you are loading the wafers you have to purge out the unwanted oxygen, because we do not want to start growth of oxide at lower temperature until all the wafers are at a particular temperature to have a uniform growth. So, we will first introduce nitrogen and we will purge out the oxygen and other gases from the chamber, only nitrogen would be there. Now, we will insert wafers, right, on a wafer holder. Wafers will be kept on a wafer holder. The wafer holder would have slits to hold the wafers, like slits to hold the wafers. So, if you see a cross section you will just see like this, right, which is shown here. So, that is why whenever we see oxide, oxide grows on both the surfaces, front and back. Oxide grows on both surfaces, front side of the wafer and the back side of the wafer, whether it is polished or unpolished, it does not matter, it does not matter. Second, now this is about, so once the furnace reaches at a temperature, let us say 1100 degree centigrade, we will stop nitrogen and we will start flowing oxygen. We will stop nitrogen and we will start flowing oxygen, so that silicon dioxide forms on the silicon wafer. Okay. That is the first thing. Second is wet oxidation. Wet oxidation. In wet oxidation there is a bubbler, this we can say bubbler, or a heating mantle is the outside, this is a heating mantle here, right, and there is a water inside the bubbler. Now, we heat this water and the vapors are created. Now, initially this valve is closed, this valve is open and this valve is closed. So, oxygen cannot pass, only nitrogen is allowed to pass, right. So, nitrogen flows into the chamber similar to this process, right. And once we reach appropriate temperature, say 1100 degrees centigrade, then what we do? We keep this open, we stop nitrogen, we start oxygen, we stop this or close this valve, open this valve and open this valve. So, what will happen? What will happen? Now, the oxygen will flow through this to the bubbler, it will take the vapor out, vapor will go up and it will reach the chamber to form the oxide. Got it? Right. So, here we are using vapor which is H2O gas, all right, to create oxide, and this is your wet oxidation. Another one is pyrogenic oxidation, where you allow the H2 to react with O2 and form H2O, and then when the oxygen is flowing you allow H2 to pass through it, react it, and then you can grow oxide. However, pyrogenic oxidation is not so popular like dry oxidation and wet oxidation. So, we will just concentrate on dry and wet oxidation, we will not consider pyrogenic, we will not talk about it later. Now, these are the actual photograph of the horizontal multi-zone furnace used to grow thermal oxide on silicon wafer. This is horizontal tube furnace, sorry, this is horizontal furnace, this is vertical tube furnace. This one is horizontal furnace 1 and number 2 is vertical tube furnace. Vertical tube furnaces are not too popular in growing silicon dioxide. So, we will concentrate on horizontal tube furnace. Now, in horizontal tube furnace there are 3 zones, a 3 tube horizontal furnace with multi zone temperature control. See tube 1, tube 2, tube 3, right, tube 1, tube 2, tube 3, 3 tube and multi zone. We will see in the next slide. You can control the temperature, you can program the temperature, right, using your system, and you can grow multiple oxide thickness or multiple thickness of oxide. One thickness can be on tube 1, second would be on tube 2, third would be on tube 3. So, the throughput increases, the throughput would be high. Now, you can see here we have wafers loaded onto the wafer holder, and this wafer holder is inserted inside this horizontal tube furnace. It is already heated, right, and you can here see that operator is pushing the wafers inside the horizontal tube furnace, right. Now, the tube is generally made up of quads, the gases are inlet from one side, gases are the outlet is on another side, right, and the silicon rod is used to push the wafers inside the horizontal tube furnace. The typical velocity of oxygen or water vapor that flows to the reactor is around 1 centimeter per second, all right. This is the typical velocity for the oxygen or water vapor to flow through the reactor. So, once we have a oxide, let us say I have silicon wafer, and what I said that the oxide will grow on both the sides because gases react with both surfaces of the silicon wafer, right. You see here both surface of silicon wafer, the gases react with both surface forming oxide on both side. So, once we have oxide grown on the silicon wafer, right, silicon dioxide. Now, we have optimized the parameter, let us say we have optimized the parameter and we have grown 1 micrometer of silicon dioxide. Okay. How you know it is 1 micrometer? How you know it is 1 micrometer? So, to understand, to measure the thickness of silicon dioxide, we have to use some characterization tool, thickness measurement tool, correct. So, what are those tools? So, let us see. The first technique is called a surface profilometer, in which it is also called alpha step profilometer, in which we use a stylus to scan the wafer and get the thickness. However, we need to perform a process before we can use stylus to measure the thickness. What is this process? So, let us see here. Let us say this is a wafer and we have oxide. Then before we use stylus, we have to create a step in the oxide. We have to create a step in the oxide using photolithography. I will teach you photolithography in the following lectures. Right now, just see that there is a step. We have removed oxide from this surface and we have retained oxide in this area, right. In this area we have removed and in this area we have retained the oxide, right. Now, what we will do? Now, we will take this stylus and we will scan the wafer with the stylus. So, what will happen? When it goes here, there is a step, right, there is a step here. So, because of this step, the stylus will bend and the corresponding bending of the stylus will be calculated and that will be your z direction, right, and corresponding to that we can know the thickness of the silicon dioxide. So, you can see here oxide etched away by HF hydrofluoric acid over part of the wafer and mechanical stylus is dragged over the resulting step. There is a travelling stage, right, there is a stylus here and there is a scanning line through which stylus is scanning. There is a 2 micron per millimeter slope, right, and you can here actually see the photograph of a styler, mirror the image of a styler here and stylus here, and you can see that it is scanning through the stage, and when it scans through the stage it can give us the we can change the speed of scanning, we can change the speed of the z direction, illumination, scan stage, zooming, whether you want to have a display at 100%, 50%, 25%, and you can calculate the thickness of the oxide. So, you can, it is very easily understand that if I move the stylus from this direction to this direction, you can see my pen moving here, right. So, from this to this direction there is a step, because of this step we can know the thickness. However, the this way of measuring the thickness of the silicon wafer comes with some kind of drawbacks, and drawback is that it cannot measure the thickness of silicon with ultra precision accuracy, precise value. And for example, with a precision of 1 nanometer or 2 nanometer or 10 nanometers it cannot do. Okay. So, it can be used for crude measurements. Now, this is still better, but sometimes in a lab you will observe that just looking at the wafer you can tell it is 1 micron or it is 0.5 micron. because the color of the wafer would change since the silicon is light gray in color, or you can say a little bit darker lighter gray or gray in color, and then you grow 1 micron oxide, you will see a greenish color of silicon. So, let us see, if I have a wafer I can show it to you. You can see this one, this is purple in color, you can see very clearly purple in color, right. So, this thickness of oxide is different in this case, thickness of oxide is different in this case. You see this one, see this is how the silicon color would be grayish. So, if I put now this one, you can clearly see a difference when oxide is grown, right, difference when the oxide is grown, you can clearly see the difference in color, right. Do not worry about the pattern, just worry about the color, silicon oxide on silicon, very easily you can identify, correct, back side is oxide of course. So, in here we have etched the oxide from the front side, here it is there, in here there is oxide on the front side, oxide on the back side, oxide on the front side, oxide on the back side, alright. Here no oxide on front side, but there is oxide on the back side. Okay. So, now what is the thickness of oxide? I cannot tell what is the thickness of oxide just by looking at the color of oxide, or if I am working from long time in a laboratory, with the experience I can tell, okay, it can be 0.5 micron, it can be 0.8 micron or close to, let us say it is 1 micron, but how accurate I am with my thickness is not possible. So, you see here the thickness determination by looking the color, relative illumination intensity, right, silicon dioxide. When you grow silicon dioxide, you can very clearly see here, because of the transparent thin film, the oxide thickness for constructive interference viewed from about angle 0 degree is x 0 equal to k lambda by 2n, n equals to 1.46 for k equal to 1 to 3. So, I can tell the difference between two films having 10 nanometer of thickness difference. However, it is very difficult to exactly differentiate 10 nanometers, but like I said, about 200 nanometers difference, 0.2 microns we can tell if it is, if we have enough experience working in the lab. So, what to do? Then to have an extremely precise measurement of the thickness of silicon, we have to use something called ellipsometer. The technique is called ellipsometry and the equipment is called ellipsometer, where there is a light source, filter, polarizer, quarter wave plate, there is a reflection, there is an analyzer and detector. The film is measured. So, after the quarter wave plate, the linearized, so after when you insert the light after the quarter wave plate, the linear polarized light becomes circular polarized, which is incident on the oxide, right, and the polarization of reflected light, which depends on the thickness and refractive index of the oxide layer, is determined and used to calculate the oxide thickness. Now, multiple wavelengths incident angles can be used to measure thickness or Ri of each film in a multi-film stack. The advantage of this particular technique is its accuracy of 1 nanometer accuracy. So, this is what we have to understand, that when it comes to measuring the thickness of oxide, we have few techniques starting from alpha step profilometer or surface profilometer. We can understand using the color of the wafer, or we can use ellipsometer to understand the thickness of the wafer. Now, in the next class, let us see what is physical vapor deposition. It is very important because we want to understand what is photolithography, but for performing photolithography, first let us see what is silicon dioxide, physical vapor deposition, then we move to photolithography. Till then, you take care, I will see you in next class.